Hey everyone, I am Austin Anderson. I'm one of Dr. Cook's TAs. Welcome to Virtual Lab for the rest of the semester. Okay, so today I'm going to be talking about experiment number 8 here. Experiment number 8 is the ideal gas law and molecular mass of gases. Okay, so the point of this experiment is to determine the molecular mass of an unknown gas after having found the weight of that gas. Okay, so to find the weight of the gas, you can actually take a syringe. When it's empty, it will weigh a certain amount on the scale. You fill it up with a gas, and it will weigh slightly different. That's due to the mass of the gas contained inside the syringe. Okay. So, today, we'll be focusing a lot on the ideal gas law and how we can manipulate it to actually solve for the molar mass of these gases. Okay. So, here we see our ideal gas law, PV equals nRT. It's pressure times volume equals number of moles you have of the gas times your ideal gas constant R times your temperature in Kelvin. All right. So we know that the number of moles in is equal to the mass of the gas you have divided by the molar mass of that gas. Okay. So you have your mass in grams divided by molar mass, which is in grams per mole. Take grams divided by grams per mole. Grams cancels out. Moles goes to the top, and you're left with moles of your gas. Okay. So we can actually substitute that back into the ideal gas equation shown here, where we have PV equals now mass in grams divided by molar mass times R times T. Okay, so rearrangement of this equation lets you actually solve for the molar mass of each gas. And this is equation 1. This is going to be one of the main equations that we are using in today's lab. Okay, so try to follow along in your lab manual as I go through this, and hopefully that'll explain things a little better. Okay, so we're going to need to know how to do calculations for today's experiment, and here is an example calculation. All right, so when using the ideal gas law, you always have to pay attention to the units. Okay, make sure that the ideal gas constant that you use is in the correct units, and everything else cancels out correctly. So if my ideal gas constant is 0.0821 liter atmosphere per mole Kelvin, I need the rest of my units to be in units of liters, atmosphere, and moles in order to make sure everything cancels out. Moles and kelvins. Moles and Kelvin. Okay. So here I have my example problem. I have a container with a gas in it, and I found the pressure inside the container is 745 millimeters mercury. The volume of the gas in the container is 20 milliliters, so imagine my container is this cylinder. The gas is filled up to the 20 milliliter mark. Okay. Room temperature in here is 26 degrees Celsius. And whenever I would weigh this cylinder on the scale, I get a mass difference of the empty cylinder versus the cylinder with the gas in it of 0.089 grams. Okay, so that means the mass of my gas is 0.089 grams. Okay, so going back to that equation number 1, we need to calculate the molar mass of this gas. Okay, so using this equation, we need mass times R times T over PV. Okay, well, I'm given pressure and volume in units of millimeter mercury and atmosphere. Millimeter mercury and milliliter. Okay, I need to convert that into atmosphere and liter in order to get things cancel out. So that's what I do right here. So it's 760 millimeters mercury is 1 atmosphere. So I didn't show the conversion, but I just went ahead and did the conversion up here. So My pressure is 0.98 atmosphere. All right, do the same thing for volume, convert it from 20 milliliters into 0.020 liters. And I go from Celsius to Kelvin, okay? So my actual final concentration, whenever I plug all these values in, is going to look something like this. I've got my molar mass is equal to my mass in grams times R times T over pressure in atmosphere times volume in liters, okay? So when I calculate that through, I get the molar mass of my unknown gas as 111.47 grams per mole. All right, so in your calculations today, these are the three different equations you're going to be using. You're going to be using the molar mass equation that we just derived, equation 2, which is given to you on page 8-3. So that is, in order to calculate the mass of your gas in the cylinder, you take the mass of the gas-filled syringe. So when this is filled with your gas, be it carbon dioxide or nitrogen or your unknown gas, you take this, weigh it, and then subtract that mass from the mass of the air-filled syringe minus the mass of the air, okay? So where does the mass air-filled syringe, mass of air come from? That's basically the mass of the empty syringe, because technically, if you look at it like this, I have a full syringe of air. I push this out, well, there's holes in this side, so air gets sucked right back in this direction. So you're basically measuring the mass of the syringe itself. Okay, I do, however, have to subtract the mass of air. So how do we find the mass of air? Well, we will use the chart given on page 8-5 to find the density of the air given today's barometric pressure and temperature, and then multiply that by the volume of the syringe to get the mass of our air. Okay. With that, I will actually move over and do the experiment. All right, hey everyone, I'm back here with Dr. Eob now, and he is going to go ahead and fill up my syringe with carbon dioxide. He fills it up to the 50 milliliter mark, and we instantly put the cap back on the syringe in order to make sure that our carbon dioxide does not escape. Okay, so now we have our syringe filled with carbon dioxide. We're going to take it back into the lab and measure the mass on the scale. All right, so here we are back in the lab now. We take our syringe filled with carbon dioxide and we zero our scale and measure the mass of the syringe filled with carbon dioxide on our scale. Okay, so it looks like our carbon dioxide syringe is 40.560 grams. Okay, so now I would take this, empty my syringe, and go have it filled up with my nitrogen and then with my unknown gas. Okay, I won't show that, but just know that I'll have to go back, get my nitrogen and unknown gas the exact same way. Okay, and as for the air, well, all I have to do, pull this to the 50 milliliter mark, put my cap on it, and weigh it. All right, here we are back with the PowerPoint presentation. So I went ahead and I measured my 4 different syringes, my air-filled syringe, carbon dioxide, nitrogen, and my unknown gas. Okay. So first of all, on your results, you need the air temperature. Okay. So the air temperature here today is 26 degrees Celsius. Okay. You're going to need to make sure and convert that to Kelvin when doing final calculations. Okay. Barometric pressure is 747 millimeters mercury. Once again, you're going to have to convert that to atmosphere in your final calculations. Okay. The volume of my syringe was 50 milliliters. And if you look on page 8-5 in your lab manuals, you will see this chart here. Okay. So according to our results in the chart, the density is going to lie somewhere between 1.149 grams per liter and 1.165 grams per liter right here. All right. Just know that there are 10 millimeters mercury in between 740 and 750 millimeters mercury. How much does the density of air increase per 1 millimeter mercury? That's a calculation you can do on your own. Just know that in between the 2 points, so 10 millimeters mercury, the density increases by 0.016 grams per liter. Okay, so I'm going to let you fend for yourselves there on calculating the actual density of the air. Okay, now here's my masses of the different syringes. My mass of my air-filled syringe, 40.533 grams. Mass of my CO2 filled syringe, 40.560 grams. Mass of my nitrogen filled syringe, 40.527 grams. And mass of my unknown gas filled syringe was 40.483 grams. Okay. One thing you might notice here, mass of the unknown gas filled syringe is lighter than the mass of my air filled syringe. Okay. So my unknown gas is lighter than air. There's not a whole lot of them out there, so that might help you in your post-lab calculations. All right. Speaking of calculations and the post-lab. So, on the calculations page, you're going to need to calculate the mass of your gas and the molar mass of the gas for carbon dioxide, nitrogen, and your unknown gases. Okay, so this is going back using equation number 2 to first find the mass of the gas. So you take the mass of your gas-filled syringe minus the mass of your air-filled syringe minus the mass of your air. Okay, so the mass of your gas-filled syringe, that's these masses right here. This CO2 filled syringe, N2 filled syringe, and your unknown gas. Here's the mass of your air-filled syringe, and you will be calculating the mass of the air using this method up here. Okay, so do those calculations. Once you have the mass of the gas, you can take that and plug it back into equation 1 to find the gas's molar mass. Okay, so here you have mass, and that should pretty well cover it for the calculations. Now, as we get to the post-lab questions, question 1 and 2 are fairly straightforward. I don't think there will be many questions there. Question number 3, you're going to have to use equation 1. You'll set this up pretty much exactly like I did the example problem at the first part of this video. You're going to use that to find the molecular mass. Once you have the molecular mass, you can use that to determine the molecular formula. Okay. Hopefully everyone here knows how to calculate the empirical formula by now. You've got 82.66% carbon, 17.34% hydrogen. Take those, turn them into grams, so you have 82.66 grams of carbon, 17.34 grams of hydrogen. Convert that into moles of each and figure out which one has the lowest number of moles. Divide both of them by the one with the lowest number of moles. That will give you your empirical formula. And then to get the molecular formula, you take your empirical formula and multiply, or take your empirical formula mass and multiply that mass by whatever factor it takes to get to the molecular mass. And whatever that factor is, you multiply it through your empirical formula. So say my empirical formula gave me a mass of 20 grams per mole, but my actual molecular mass was 40 grams per mole. So 20 times 2 equals 40. That means I have to multiply everything in my empirical formula by 2 to get my molecular formula. So say my empirical formula was C2H8. My molecular formula now is going to be C4H16. All right. So post lab number 4 and 5, just know that density is equal to mass per unit volume. Okay. So we can actually substitute density into our ideal gas equation. So it's the ideal gas equation it's equation number 1 that we have already all right. Now for post labs 4 and 5, just know that the density is equal to mass per unit volume. Okay, so it's mass in grams divided by volume in liters. We can actually substitute this back into equation 1. We see we've got mass and volume in equation 1. We can take those out, substitute density in. So now we have the ideal gas equation in terms of molar mass of the gas and density of the gas. Okay, so you can rearrange this however you see fit to solve for problems number 4 and 5 in the post lab. And that pretty well sums it up. If you listened to the entire video lecture, I applaud you. Thank you. Keep doing that. I will not always cover every little thing in the PowerPoint, so you need to be listening along as I go through these video lectures.